Okay, so I think so we can start. So last two classes, what we have been doing is we looked at this problem of Brownian motion in potential or free particle, and we have looked at this problem various ways. Like, so we looked at this description, Landsberg description, then we looked at this Fokker-Planck description. Then also we looked at this. Okay, we said that okay, this Fokker-Planck equation can be mapped to a Schrodinger equation, right? And so these mappings are useful because sometimes you know the answer in one of the problems. Maybe you have done that problem before, or somebody else might have done this problem before, and then you can just get those answers. So that's why these connections between different kind of systems is very important to know, right? So today we are going to do one more way of looking at this problem, and that's called path integral description, right? So you know that in quantum, so it should not be a surprise because you saw that in the yesterday that okay, so that Fokker-Planck equation can be mapped to the Schrodinger equation, and you know that quantum mechanics there is a description of this path integral. So there should be a similar description here, right? Or in fact, it was I guess here, and then it went to. So yesterday, so we said that okay, so if I just look at a trajectory, okay, so this is my time, and this is my position. Suppose I just start with some position x0. So these trajectories are random, right? So it goes something like that. If I just discretize this time, it's something like that. It need not be equal, so this is like that. So what determines this thing? These are these jumps, right? These are these random jumps. So therefore, if I just specify you these jumps, if I tell you that all the jumps, so that specifies one trajectory, right? For example, let's look at this equation. So this equation was in the continuum limit. This is equal to so that was the equation, right? Or let me just put it here. So where mean is 0, and this eta is a Gaussian random number. Okay. So if in a given realization of the trajectory, so if I tell you all the etas, right? So the eta 1, eta 2, suppose just think of it, I'm just writing down this equation in a discretized way, right? So that specifies the whole trajectory, right? So therefore the probability of this trajectory, whatever the weight associated with this trajectory, I can find out from the weight associated with these noises. Right? Suppose just consider a discrete version of this problem, right? So what is a discrete version? So discrete version, it says that okay, let's just look at x tau minus x tau minus epsilon divided by epsilon. So epsilon is my delta t. So this is like minus pi gamma plus noise in this discrete version. So how am I going to evolve this? So initially, let's say my x at 0 is equal to x0, then I can find out x1, x epsilon, right? So what is x epsilon? So the x epsilon will be x0 minus epsilon times plus 2. And so on, right? So this one is, it also has an argument. This argument is at epsilon. Then I'll find out x 2 epsilon, right? So that's given by x epsilon plus epsilon times and so on, right? So in this one, this eta epsilon, eta 2 epsilon, these are the random numbers. So therefore, if I want to find out what is this probability or the weight of this whole path for a given path, so that will be determined by the weight of this one, right? So for a given path, so therefore what I will have, I'll have a set of weights. So what is the distribution of this weight? Since each etas are independent, right? So therefore this will be product of Gaussian distributions, right? So this will be product of Gaussian distribution, and for each guy it will be eta epsilon square half sigma square. So where sigma is the width of this distribution, right? So this is basically 2D, and then since I have discretized it, it will have a square root. So this one means that P of the joint distribution of eta epsilon, eta 2 epsilon, eta and epsilon, the joint distribution, right? So the u prime x, the x is at epsilon, so there is an argument, so this is at 0. So this argument, I am going to come back to this argument. So for a time being, you just leave it there. So this is the x basically, so I'm going to come back to this argument. So this is basically just, it depends on the path, basically where you are, right? So because this x is evolving, okay? So we'll see what argument we are going to put there, okay? But it's something like this, okay? So now this distribution is, since these are independent, so this will be product of Gaussian distributions, right? So forget the normalization for a time being. So it will be something like e to the power minus 2 sigma square eta epsilon tau square at that time tau, and this is product of all taus, right? This is basically, so what I mean is that this will be something like that. Eta epsilon at epsilon plus eta epsilon at 2 epsilon plus right? It will be something like that. Because these are independent, so I can, independent distribution is just the product. So now if I want to write down in the continuum one, this sum just becomes an integral, right? So therefore if I write down in this continuum one, so P of Now this whole weight, so I am going to write it as eta of tau, where tau goes from 0 to t, right. So that becomes the same one, this is 2 sigma square, exponential of minus 1 over 2. So what is sigma square? What is the width of the noise, variance of the noise? So that's 2d, right. So this is 4 d 0 to t eta square tau, right. So this sum, it has become this integral, right. So this is what I will write it down. So this gives me a weight of a given noise realization, right. But what I need is not the weight of the noise realization, what I need is the weight of the path. So from there, I have to go to the realization of the path. Right? So from there, I have to go to the realization of the path. So what do you have to do? So now I have to go to the realization of the path. Because what I need is what is the weight of this path. So as you saw from these equations, I can go from one variable to the another variable. Right? Because x0 is given. If you give me all these etas, I can tell you what are the x's at various times. I put this value here, I can do that, right? So therefore, this one, I can go from the noise realization to the x variable. So what I am going to do, I am going to just use this equation. Right? But as you see that if you go from one variable to the another variable, there is a Jacobian of the transformation. Right? So there will be some Jacobian, so which we are going to find out what is the Jacobian, and this one I can just put it 0 to t d tau, and this one I can just substitute this equation. What is the equation? This equation is dx d tau plus u prime x by gamma. Right? So now this one, so we have to compute the Jacobian. So we are going to compute the Jacobian, but before computing the Jacobian, so let's just look at the things inside. Okay. So this, so let's look at this one. So we have this 0 to t dx d tau plus u prime x by gamma whole square. So let's just expand it. So we'll have terms d tau dx by d tau whole square plus u prime x by gamma whole square plus 2 dx by d tau u prime x. Right, I have just opened it square. So this one, there are two terms, d tau. So this one is keep as it is. So now let's look at this term. Dx by d tau. So what is this one? U prime x. So that's a derivative with respect to x. Right? So what happened to this one? Dx by d tau. This one is 1 by gamma du by dx. So let's just put it gamma constant. So what is this object? Yes, but you just look at this integral. So this is the integral over tau dx by d tau and del u by del x. So this is a complete this thing. So I can just write as dd tau of the u of x of tau, right? Because u is a function of tau through x, right? So this is like a dd tau of u of x of tau. This is an integral over tau, so I can just carry out this integral. If I carry out the integral, what is going to happen? It's just going to give me the boundary terms. U at x t minus u at right? So this is what I'm going to get. So this is fine. So this is going to sit there. So now we have to find out the Jacobian. And then we are going to put everything back into the this expression. So let's just give this expression mark somewhere so that we don't. So we are going to put everything here. So we have this thing here, and then we need an expression for this z, right? So what is this Jacobian actually? So suppose you go from variable x1, x2, x3 to y1, y2, y3, right? So what is the Jacobian? So Jacobian is a determinant of a matrix, right? So what is the variable? You are going from this variable to that other variable. So these Jacobians will be like, general term will be like d eta by dx, but at various times. Right? So I have to find out all the, these are all, so I have to find out all these elements. For example, I have to find out that so I have to find out all these elements, right? So let's write down this equation again, the general form, the discretized version of the equation, and then we go to the continuum one to find out Jacobian. So what is eta epsilon of tau from that equation at some value tau? So this will be x at tau minus x at tau minus epsilon divided by epsilon, right? So that's this one plus this guy, right? So plus this guy, so that guy becomes plus. So let's just call it f of x is minus u prime x, so that becomes 1 by gamma times f of x at tau. right? But which tau should I take now there, right? Because this is a path, this is a section of a path which is going from x at tau minus epsilon to x at tau. Okay, so one of the way to actually choose this thing is you take the force at this point, you take the force at this point and take a half of it. Okay, so it says that you take F at x at tau plus F at x at tau minus epsilon and take half of it. Okay, or you can, when your epsilon becomes small, it doesn't matter, or you can also say that I can take the force at the midpoint. Okay, so both becomes equivalent. Okay, so this is what you are going to do. So taking this sum of these forces instead of taking only one of them, so this is called Stratonovich convention. Okay. So now given this, I can find out the elements of this matrix. Each eta at tau depends on x's at 2 in this thing, right? Because I'm going to take the derivative with respect to these two x's, right? So what are for a given eta at some tau, what will be the non-zero elements? I can either take a partial derivative with x at tau, or I can take a partial derivative x at tau minus epsilon, right? So it will have a diagonal element and it will have a lower diagonal row, right? So what is tau x tau? So this is 1 over epsilon minus 1 over 2 gamma f prime x at tau, right? Because that's a derivative with respect to the argument. So similarly, this other one, okay, let's just write down this one again. So this one, let's just take out 1 over epsilon outside. So what I have is 1 over epsilon by 2 gamma. Okay. So these are the elements on the diagonal. Right. So these are the elements. These elements will be there. So it will have all elements on the diagonal. Okay. So what is the other one? So other one is taking with respect to so this gives me minus 1 over epsilon and minus 1 over 2 gamma f prime of x at epsilon. So these are the elements on this one, right? And all the other elements will be 0 because there is no, it only depends on only 2 times. One is at that one and one is at a previous one, right? So there are no other elements. So then I know what is the determinant of this matrix, right? So if you have a matrix where you have only the diagonal element and one off diagonal element, what is the determinant? So it's just the product of the diagonal elements, right? So therefore J, the Jacobian, So what is the Jacobian? So Jacobian is the product of the diagonal elements, right? So this is product over tau at different times, and then okay, there is a 1 over epsilon coming from each of those. Let's just epsilon coming from each of those. Then 1 minus epsilon by 2 gamma f prime x. This is what I have, right? So there are of course lot of these epsilons, but so what we can do, we can forget this epsilon hanging here, because so epsilon is some fixed number, so okay, it's very small, so it will be like a very distinct. But what we are doing is we are putting as a proportionality distinct, right? So we can just absorb it here, whatever this distinct. So I don't need to worry about this epsilon. So what I am going to do at the end, I am just going to make sure that it's a normalized distribution. Right? Is that point clear? See, this distribution is proportional to this one, right? I have not given you what is the proportionality constant. So how are you going to determine the proportionality constant? You just by the normalization. See, I have not even given you all the normalization of each of these distributions, right? So those are also here. So instead of putting them explicitly, I just kept it as a proportionality distinct, and that proportionality constant I am going to determine later. So I might as well absorb these epsilons in the whatever the normalization constant I had earlier, right? So everything I can just put it there. So therefore, I don't have to worry about these epsilons anymore, right? So if you didn't have this u prime, then what you would have got, this your Jacobian would have been just 1, right? So there is no, the Jacobian of the transformation is just 1, okay? So the Jacobian comes through only this potential, okay? So therefore, I am going to forget this epsilon, and I just put again a proportionality constant, and I am not going to talk about these epsilons. Which one? This one. This is not a diagonal term, this is the off diagonal term. Yeah. It's not 0. But if you have a matrix, so if you have a matrix, let's just compute this matrix. A, B, C, and then 0, 0, then alpha, 0, 0, beta. So I have the diagonal and the off diagonal, and all the others 0. So what is the determinant of this matrix? Right? So you take this one, but when you take this one, then this becomes 0. So the determinant of this matrix is just A times B times C. It doesn't matter what is there on the off diagonal term. So you just have only one off diagonal row where these elements are given by this one, right? So now this is what we have. So this one therefore is equal to, again what I can do, I can put this thing to the up, right? So this becomes summation over tau and log of 1 minus epsilon by 2 gamma f prime x of tau. Now I am going to take epsilon going to 0 limit, right? In that limit, this summation becomes a integral. So this, what is the expansion of this one? The first one will be epsilon by 2 gamma f prime x of tau. then the next one will be order epsilon square when you expand this log, right? So therefore, if I take now epsilon going to 0 limit, so this one will be the d tau in that integral, and all the others are going to become 0. So therefore, this one becomes 0 to t, there is a minus sign, minus 1 over 2 gamma f prime x of tau d tau, and f prime is u prime. So therefore, this becomes equal to exponential of 0 to t 1 by 2 gamma u double prime of tau. So now I have all the terms. I have this one, I have the Jacobian, so I can just put everything in this one. I'm saying we are worrying, but it's there. I have not told you anything about this one, it's there, right? So this will be given by the normalization of the distribution. It's there. Finally, whatever this thing, that one, there is a epsilon tends to 0, there is a normalization which also depends on epsilon, right? Because, right? So, but everything I don't have to worry because it will be just given by the normalization of the distribution, right? So now, what is the let's just write down everything. So therefore, my p of x of tau, that's given by, so this one means basically that the whole all the x of tau, okay? So that's given by exponential of minus 1 over, okay. So before that, epsilon. Yeah. Yes. Yes. So epsilon is your d tau. I could have just called it d tau. No, instead of calling it epsilon, I could have just called d tau. Right? So this is what you have. So now, so what do you have? So this one, so there is this boundary term that we can just write it outside, right? From which is coming from this one. So let's just write the boundary term first. So what is the boundary term? So there is a 1 over 4d, and then this is 2 by gamma. So 1 over 2 gamma d u xt minus u x0. Okay, is that term familiar? Huh? Yes, 2 kVt. But is this term familiar? So that is the same term we got yesterday when you went from the Fokker-Planck equation to the Schrodinger equation, right? That this g of x which you are supposed to compute, so that gave this term, right? So what is the next term? So next term is exponential of minus 1 over 4d 0 to t, and then Can you just tell me terms? D tau. So there is a term. There is a term del x del tau. Okay, then there is this term plus by whole square. Then this one comes with minus, right? Since I have taken out 1 over 4d here, so this should be multiplied by 4d, right? Or what we can do, okay, let's just write down this term. So what is the term? 4d by 2 gamma. This 4d comes from that 4d, right? That minus comes from because there is a plus sign. And then u double prime. This is what I have. This is what I have. Now let's go to the quantum mechanics, right? In the quantum mechanics, so your is given by, so this is the evolution, right? So then you know that at psi t, it's given by exponential of minus I by h cross h t psi 0. Okay. So this one, therefore you can write, if you want to write down in the position basis, right? So there will be a x here, you can insert a complete basis inside, right? So x0, integral over x0, right? And then I0, right? So this object, what is it called? That is just a quantum propagator, right? So this one is called the quantum propagator. So it basically, so this is the Green function solution of the Schrodinger equation, right? So this one is given by x e to the power minus I h t x0. And this propagator in the quantum mechanics is given by a path integral, right? So which is equal to all path right? This is given by this. So where this is the Lagrangian, okay? So this is the Lagrangian, which is half m dx d tau whole square minus v of x. Right? So this is the Lagrangian in the. So therefore, let's look at the quantum propagator. So the quantum propagator what we have is that's equal to that's not visible. Okay, so okay, let me just write it that on that side again then. Okay. So let's just put a subscript Q for quantum, right? So zero. So what was that? So exponential of I by h cross 0 to t d tau half m dx d tau square minus e of x. Is there anything else? Yeah. Yeah, sorry. So what is this? What does this integral mean? What does this one means? So it says that see, this one is again you have this full path, right? So I am integrating all the midpoints except keeping x at 0 equal to x0 and x at t equal to x. Right? So it could have gone through various ways, and I am integrating all the intermediate paths, right? So all variation of the path. So this also just goes from x at 0 equal to x0, x at t equal to x. Okay. So now this one, let's just the inside thing. Just look at. Let's make a slight this thing. So what we do, let's, because this tau is just a dummy variable, right? So I just make a change of variable and call that I by h cross tau is my t prime. Okay. So then what is this one? So this goes from 0 dt prime, I by h cross d tau becomes dt prime. So what is the upper limit? Upper limit becomes I by h cross t. Now this one half m dx dt prime, but then this tau there is a t prime, so there is a minus I h cross down. So this gives me 1 over minus h cross square, and the other one is still same. Okay. So this one 0 to t dt prime. So this one, let's just take a minus sign out. Minus, let's just write this term 2m by 4 h cross square. I just multiply 2 on both sides, and then let's just write down the rest. So this is dx by dt prime whole square. Minus sign is already out, but I have taken out something here, so I should just put it there because it didn't have anything. So what I should put is minus 4h cross square by 2m this is my quantum propagator, right? So which is given by this one. Becomes a plus, right? So now let's look at the let's look at the this one. So here also I want to find out the propagator because this is the weight of the full path, right? So now if I want to find out that you go from x0 to x, I don't need anything in between, okay? So I need to integrate all the intermediate points, right? So therefore, when you do, so xt x0 0, right? So this is proportional to, you just do all the with keeping x0 x, right? So you had this object which is actually you could have taken it outside. So this one, because that's the endpoints. So this one was just 1 over 2 gamma d. This becomes u of x minus u of x0. That's, you can also take it on. And this one e to the power minus 4d 0 to t d tau. Let's write down this one, dx by d tau square plus, let's multiply by 4d and I'll divide it by 4d. So then, what is this one? So I have to divide by 4d. So this is u prime x whole square divided by 4 gamma square d minus that 4d cancels, so u double prime x by 2 gamma. Okay. So now you see that this term, this guy, is exactly like that one. If I make a change of variable, if I make a change of this thing, I h cross this goes to t, if I make it n h cross square by 2m goes to d. Right? Because this one becomes 4d, this becomes t, this becomes 1 over 4d. Right? So it's exactly same as that one. Okay? So therefore, this propagator, the classical propagator for a particle is given by exponential of minus 1 over 2 gamma d u x minus u x0 times the quantum propagator. So what is the quantum propagator? X, it goes from x0 to x with a Hamiltonian. Where is this one? This one, right? Exponential of minus, but when I went from there to here, I had to make a change of variable. I by h cross t goes to t. So this just becomes minus ht x0. So where your Hamiltonian is now is just the quantum Hamiltonian with a potential which is this one. So your h is, so let me just, here you can't see it, maybe I'll just, okay, let me just plug it here. So now your h is just minus s square by 2m, which is d. So your Hamiltonian is basically d plus v of x, and v of x is given by this one, u prime x whole square by 4 gamma square d minus u double prime of x by gamma. Okay, so this is what it gives. So let's do an example why it's useful, this mapping. So this is just the now classical propagator. It just basically it says that the particle goes from x0 to x in time t, right? This is just the propagator we have evaluated yesterday. So let's just consider an example now, okay, which is the particle without any potential. We already know the answer. So let's see if we can just find out the answer from here, right? So let's consider the case where there is no force, there is no potential, free particle. So what do we have? So is this clear, or do you have any questions so far? Yeah? No, you got a wrong answer. Yeah, it's not problematic, but it's the way it is. Like even if you go to the path integral, for example, if you like quantum mechanics, when you discretize, there's a way you have to discretize the path integral, right? So it's basically essentially the same in this thing. Okay. Yeah. So you know that. Okay. So you know that finally, okay, you try various things, but you know that okay, this one will give you the correct answer because this one you know from that other way of doing it. So yesterday we did this one. So then you know that when you go to the quantum problem, this is your Hamiltonian, right? And here you say, see, otherwise this term would have been something else, right? This instead of this half, whatever you choose, it would have been here. It depends. That's what. Yeah. So you could have taken alpha and beta here with alpha plus beta equal to 1, right? So then you'd have got here alpha. So I do not have any. Yeah. Okay. So see, the point is that I guess you can take any other way of discretization, but then you have to also find out what is the way to write down the Lagrangian, right? Because when you go from the Hamiltonian to the Lagrangian, this kinetic energy minus potential energy works in a certain convention, right? So you have to make sure that basically I think equivalent to basically using the same convention. Yeah. But another way of doing it that, okay, you can take something here, but then you have to modify the Lange equation, right? So that's just like even this problem arises because if you have a multiplicative noise, I think David Dean will probably mention this. See, if you just take this equation and, so what I'm saying is that if you suppose you have something in front of the noise which depends on x, right? Like diffusion coefficient, for example, is a function of the space, right? So if you simply take this equation, it will give you it may give you the wrong answer because you know that if you take this equation and use your Ito way of writing, so it will give you a wrong answer because you know that finally in your Fokker-Planck equation, the diffusion coefficient, right? So it should come something like, so what do we have? dp dt, this is minus del x of the current, right? the continuity equation. So current is one is of course your force term, so which is just whatever F by gamma times P. Then your diffusive current, so that's d of x del x of P, right? So this diffusion coefficient comes somewhere in between. But the way we derived yesterday, so the diffusion coefficient comes within both the derivatives, right? So if you want to use that convention, basically what you have to do, you have to basically write down a different equation. So there is a drift term coming from this thing, which is there. So that extra term takes care of this. So this bit, this thing. So I don't want to get into this thing, right? But you can actually go from the one to another, but then okay, you have to modify those equations. Okay. So where are we now? We basically have. Okay. So let me just write down this one. So this is the equation. We should put it in box. So we have this one. So we have this propagator, classical propagator, which is given by this one, then the quantum propagator with I by h cross t replaced by t, and where Hamiltonian is given by this. So let's take this example of free particle. So there's no force. Okay, so we want to find out. So what is a Hamiltonian free particle? Just only the kinetic energy, right? There's no potential energy. Right? Only the kinetic energy is on. So now, zero, this is, this term in the prefactor doesn't come because there's no potential, just x p. Now what are the energies for a free particle? So if I write down in the k basis, so this will be dk prime. If I write down the momentum basis, so this one x k prime x0. So what is this element? Is a matrix element. So what is this one? So this is a diagonal now, right, in the energy basis. So H is just H cross square, okay. Ek is by 2m, right? So this one is, what is this? Delta k minus k prime e to the power minus h cross square k square by 2m t. Or what is h cross square by 2m? It is just d, right? So therefore what we have just only one integral, because one cancels by this delta function. What is this object? This is just the wave function, right? Free particle wave function. So this one is depends on, okay, well, plus ikx minus ikx doesn't matter. So it's okay, minus ikx by square root of 2 pi. That's the notation. So this one gives me d k square t e to the power I k x0. Now, right? So you can do this integral or you don't have to do this integral, you already know, because this is just the, okay, so this one is dk e to the power minus ik x minus x0 e to the power minus d a squared t. So yesterday we saw that this was the characteristic function for Gaussian, and you see that this is just the inverse Fourier transform, right? So therefore this one will give you so this will be half, so that multiplies with 2, right? So therefore this, what is the variance? Variance is 2d. So this one will give you e to the power minus x minus x0 whole square by 4 dt by square root of 4 pi. Okay. So this is the answer we have obtained before. Okay. The usefulness of this one is that now you can actually use for another. Suppose you know this eigenstates of this Hamiltonian. Suppose you have solved this problem in this thing. You can just insert these states here and you can just find out the answer. Right. For example, in the harmonic case, it would have been, okay, there is a potential, there is a quadratic potential, there is a plus some shift because double derivative takes away this one, and that will give you basically these are the eigenfunctions of this quantum Hamiltonian, right? And yeah, similarly. Yeah.
But like outside of the preparatory and like in this combination present in advantage.
This is a another way of looking at it. For example, if you have a particle in a mod potential, something like that, you know the quantum problem, right? That quantum problem you know. So these are given in terms of airy functions, right? So it says basically that because since quantum mechanics, many of these problems are well studied, right? So you can immediately see that, okay, this is a problem, something I know from my undergrad, and I can just read out this thing. Instead of, another way to do is you start with the differential equation, whatever this thing, and you solve the differential equation. You give it the same answer. Because at the end you are solving the same differential equation or almost similar differential equation, right? Either you are solving for the quantum problem or the, this one, almost similar differential equation, you have to solve that, right? So this one is basically, you identify the problem immediately. Oh, this problem I have seen it before. And that's useful sometimes.
But if there are other systems where you can solve it in this way, but
I mean, if you can solve this way, you can also solve it there.
I mean, like, is it like...
Right, because now I'm saying that finally is the same differential equation. If you know this solution, because yesterday I have showed you that how to go from the Fokker-Planck to the Schrodinger equation. You can do the same mapping starting with that one, this one. And now you know how to solve the Schrodinger equation and you go back.
But you can't solve more problems. So, like, can you solve more complicated problems?
No, this is a way to look at a complicated problem. Something looks, made the problem simpler to you, looks simpler to you basically. Okay? Or sometimes it's useful way to formulate a problem. See, otherwise some complicated potential, we'll see again some other examples. I don't know, we have some time. You can solve some another way, but sometimes it's okay, oh, if I just write it this way, I know this problem and I can just immediately write down the answer. Right? So this is sometimes basically instead of spending few days to find out how to solve your differential equation, right? Go to Gradstein or something, find out all these things. Sometimes it basically, oh, this is a familiar problem. I know which book to look at it and I can write down the answer from there. So this is like a, it makes the problem familiar to you. Okay, but it doesn't, yeah. Or sometimes it also, suppose you are doing a new problem, right? Sometimes it's easier to formulate the problem like this. See, once you write down the equations, right? You have to solve it. So this is even sometimes another way to write down the equation, because suppose you know that this thing is given by that. So you know, oh, this is the Hamiltonian, right? So this one is basically the quantum propagator. I know what is the equation I should write down, right? That's just the green function for the Schrodinger equation, right? So I can immediately write down the equation, right? Instead of going through, instead of computing all the various moments and this thing. So that's why these problems, it's not that you can solve many ways. Sometimes one way looks simpler, or sometimes one way, it's easier to present one way than the another one. So therefore it's useful to know various techniques and then connections basically. Okay, so next I have I think about 20 minutes. So far so I guess 20 minutes, let me just see. So far what we have been doing, we're just releasing this particle from here and then finding out what is the final point, right? Where is the particle? There are other interesting questions you can ask, right? So one of the questions, for example, suppose, okay, say one-dimensional system, so suppose you have this line and so this is your one-dimensional line, right? And let's say this is your home at the origin, right? And there's some deadly chemical, this thing, it was released here, right? And when the chemical, and this chemical, these are some molecule, they're just diffusing. And whenever this chemical reaches here, you die, right? So then you might ask, how long does it take for me to die, right? Or how long do I survive? Okay. So these are the questions, other interesting questions, right? So it's not that just a simple endpoint, something else. Or you might ask that, okay, this is your home somewhere, maybe there somewhere your home, and you are walking in the night after coming from the bar, so you don't know which way to go. And suppose there is a huge cliff and your home is somewhere there. You might ask, okay, if I start from here and I don't know which way to go, I'm just doing a random walk, what is the probability that I'll fall down from the cliff? Or what is the probability that I'm going to survive? Okay? Or what is the probability that I reach my home before falling down? Right? If I fall down, I'm not going to reach down. So these are the questions. So these questions are called survival probability, and first they are related for spaces time. Okay, so let's just formulate the simpler problem now, which is, now I have this. So this is my time, this is my space, and suppose I start from some point x0, right? So there is a cliff here. So what is the probability that I start from here and reach at time t some position x without crossing this line, right? So it is, so the equation is still same, dx dt is equal to eta t, the same equation. So what you are going to do, how do I going to solve this problem? Now this is a different probability. So let's call it E sub A. So it's, what is the probability that you reach x at time t starting from x0 at 0 without crossing the origin? Okay. So this is what you have to solve. So what is the equation this PA satisfies? Everywhere there, what is the equation it satisfies? If it's here, it doesn't know whether this cliff is there or not, unless it comes to the cliff, right? Because the Brownian particle doesn't know. It satisfies the same equation. Satisfies the same equation. Except now the boundary conditions are different, right? So because giving the equation is not enough, you also have to give me the boundary conditions. The same equation with different boundary conditions will give you different answers, right? So what is the boundary condition without this one earlier? When we solve this free particle, so what is the boundary condition? The probability vanishes at infinity, right? Earlier, right? Because if I start from some point x, 0, and at a finite time I cannot reach infinity, right? So that was the boundary condition earlier. So now my boundary condition will be different because still I cannot reach infinity at finite time. Also my probability should vanish at x0, right? So therefore I have two boundary conditions now. P of x goes to infinity that should be equal to 0, and P at x equal to 0 at any time, this should be equal to 0. So I have to now solve this equation with these boundary conditions. So how are you going to solve this? You know how to solve this with different boundary conditions, right? So what will you do? You can again solve various ways, but okay, maybe one of the way you can do is, okay, again take a Laplace transform with respect to time. So then it's a, so we had already that equation last time, right? And you took the Laplace transform. We have to find out that we have to give the initial condition also. So what is the initial condition? X equal to 0, x0, 0 is just delta x minus x0 because it just starts from this thing. And yeah. So now with this one you have to solve. So you can solve this problem, right? So try to solve this problem. So you took a Laplace transform with respect to time, then it's a differential equation in x, and x similarly you can find out the, you can take a Laplace transform of these conditions, it will be still the Laplace transform will be 0, and you just solve it, right? You have solved similar equation, no, in electrostatics, like you have solved Laplace's equation, Poisson's equation, right? You just like just look at the book objection if you have not done so, right? Because you should just do it. Yeah. But okay, so this is just a, because once you take a Laplace transform, it's just a second order differential equation, no? I mean, there is nothing much. There will be some exponential solutions, and then you have to just find out the coefficient by putting proper boundary condition. Only thing you have to make sure is that there will be a delta function there, right? When you take a Laplace transform of this equation, right? That's what we did when you the first class thing, when you took a Laplace diffusion equation, there will be some delta function. But you know how to solve a differential equation with a delta function, right? How do you solve? Green function is the differential equation with delta function, but how do you solve the? So what you do, okay, so let me just tell you. Yeah, so what you do is, suppose now you have this one, this is your 0, this is x0, this is infinity. So in that solution there will be some delta function. So in the delta function is 0. So you solve in this range. So it will be some exponential solution. So you will be P of P tilde of A will be some A e to the power minus something x plus B e to the power plus something x, right? You solve in this range. So this range, your P of A will be C e to the power minus something to the power x, and there cannot be any positive term because your solution should vanish at infinity, right? So now that takes care of one, and there is one boundary condition here which says that P should be 0 here. So this is at when you put x equal to 0, A plus B should be equal to 0. And then there is 1 here. So you see that if you just integrate this equation once, it says that the derivative should be discontinuous at this point. And that it takes care of the result. So we'll solve something. So these things are function of S, your Laplace variable, and then you have to invert it back. Okay, so you have to just sit down and do it. So that's one way of doing it. Okay. Now, maybe you can just do it in the tutorial, because since I think we don't have much time, let me just. So what is the survival probability now? The survival probability. Okay, so let me just write down the solution. You can verify that. So this one, so this is also given by something called image method. It just says that basically this path, all the paths going from here to there, some paths are going without crossing them, and some paths, there are some paths which are going crossing them, right? And that this probability PA is basically the probability where you subtract all the path which crosses this one, right? So what you can do, that's equivalent to, because there is a homogeneity, all the paths which goes by crossing this one, there is a one-to-one correspondence which goes from a path which goes from minus x0 to, basically you just write down there and it goes there, right? So all the paths which goes from x0 to x by crossing this one, for each of those paths, you can write down a path which goes from minus x0 to x, right? Because whenever it crosses, the first crossing, you can reflect this one to the other side. So those would be path going from there. So therefore, the solution is your old solution minus the probability that this particle goes from here to there. So that's the same one with a x equal to minus x. So now you can verify that, okay, you can easily verify that that solves that equation, because it solves the differential equation. Where did I write down? This one, because for any x, this is a solution for the differential equation, right? It satisfies the boundary conditions. If you put x equal to x0, then what do you have? It's 0. No, yeah, if you put x equal to 0, that gives you 0. So that satisfies this one. And you see that when x goes to infinity, that's 0. Right? Now you know that these differential equations, they have unique solutions. So if you can write down a solution which satisfies all the boundary condition and initial condition, that's the only unique solution. So therefore, this must be the unique solution, right? But you can systematically derive it from that problem. Okay. You can also now derive it using your path integral thing. So what is the path? So this is your propagator, right? This is the propagator you are writing with the absorbing thing. So what is the corresponding Hamiltonian? You can again write down the whole path integral thing, except that you have to put a condition now. So what is the condition? The condition that at each time this x tau must be positive, right? So in this case, it's the same one, except that when you write down this one, there will be an extra condition which says it's basically product of x taus, right? It just says that, okay, this condition. So this is why this path integral formulation is useful, because all the other thing you can just put as a condition to the existing thing. And this one now you can actually put it in the top, right? So that's same as integral of log of the theta function, right? And when you see that, put it there, there will be a correct sign. Yeah, so you know theta function. So theta function is a function, it's a Heaviside function. It's called 0 for x less than 0 for x greater than 0. So this is called Heaviside. So apparently he is the person who wrote down your Maxwell equation in the current form you know. It's not Maxwell wrote down this in this vector form where you just have 4 equations. I think apparently he is the guy who wrote down. Okay. So now, then what is the log of this function? It's just either 0 or minus infinity, but then when you put it there with the correct sign, so this will become plus infinity. So now you have a classical quantum problem where you have an infinite barrier. So you have your quantum problem is infinity for x less than 0, 0 for x greater than 0, and free particle. So this guy is just x e to the power minus ht x0, where h is given by the kinetic energy plus the potential term, which is this one. So what is the wave functions? What are the wave functions? It's free particle, except there's an infinite thing on this side. So the wave function must vanish here. So what is the wave function? These are sine functions, right? So this functions is sine kx with the proper normalization. What is that for the sine? Square root of 2 by pi or something. Let's see. Yeah. Okay. Yeah. So now this is an energy, is the same. This is dk square by dk square. Okay. So now you know what is this thing, dk. One guy will give you 2 by pi sine kx, other will give you sine k x0, and then this one is e to the power minus d k square. Right? This is the integral you can do. It's actually even in k because this gives you minus sign, this gives you minus sign, so this thing. So you can actually extend from minus infinity to plus infinity. And sine you can write as a e to the power ikx minus e to the power minus ikx. So you'll see that it's almost similar to that other one, except now there will be two terms, and those two terms basically gives you these two terms. Right? You can just compute it. It's just a two-line calculation. You just do it and you'll find it. Now, what is the survival probability? But let me just take 10 minutes if you are not terribly hungry, I guess. Okay, so let me just tell you what is the survival probability. Survival probability is that the particle survives. You don't care where the particle is at x, at time t. So your survival probability, which is a function of x0, which is the starting point, this is just integral of this object over x, 0 to infinity, bx, ba, xt. You can compute this, and what you will find, the answer is that this is given by it's just a simple integral, right? You can see actually why you get this, because it's just the integral of Gaussian, and integral of Gaussians are error function, right? So you see that it's at large time, survival probability goes like 1 over square root of t. Right? So this is the survival probability. Did Abhishek talk about this one? No. Okay. So you will see that even if you do the random walk, this scaling, that it will go like 1 by square root of n. Okay. Then the first process, let's call it, it's a function of t given x0. So this is, what is the probability? So this is the probability that the particle hits x0 for the first time at its origin for the first time at t starting with x0 at. It says basically this particle moves. When is the first time it hits this one? It's the first space's time, and what is the distribution of that time? So what happened? So this one is, this time is equal to, so let me just write down first as x0 t minus x0 t plus. So it says that, okay, this is the probability that survives up to time t. That's the probability that it survives up to t plus delta t. The difference must be that it did not survive, right? And that's the one that it hits the origin. So it did not survive. So therefore, this first space's time probability is given by minus del s. So now you can just compute from there. And what you will see, you can find out, it will be some, so is the, so this one, what is that? Error function, so this will be x by square root of 4 pi d 1 by t to the power 3 by 2 exponential of minus x0 square pi. So this 3 by 2 you can see, because if you take a derivative of this 1 by square root of t, that becomes 1 by t to the power 3 by 2, right? So how does this function look as a function of t? There is a characteristic, so this is x0 t, there is a characteristic time which is basically x0 by 4d, okay, till that time. So you know this function, right? What is this function called? Have you seen this function before? Huh? No, I'm saying that this part as a function of t. Yeah? What is the function? Just forget about this other one, you just call it t by t star. Some t star. So this function is basically exponential of minus 1 over something, right? Exponential of minus 1 over z. What is this function? You must have seen in your complex analysis, right? You hear about all these singularities, right? So there is something called essential singularity, right? So this is an essential singularity this function has. The property is that this function, when t goes to infinity, what is the behavior of this function? It reaches 1, right? But near origin, this function, all derivatives of this function vanishes. So if a derivative of a function vanishes, what happens? It is just slower and slower, right? If you see near x equal to 0, x goes like this, x square goes like this, x to the power 4 cube go like this, x to the power 4 go like this. So now imagine a function where all derivatives are 0. So it's almost flat. So this function basically goes almost flat and then it sharply rises. So it basically goes something like that. And then after some time this term becomes 1. So then this term takes over. So what is the behavior of this one? This is just a power law, right? So this one, so it just goes something like that, and then it has a power law tail. So this one goes like 1 by t to the power 3 by 2. This gap here, which is given by this function, so if you do a discrete random walk, discrete time random walk, what should happen? You can ask the same question. I start from some position x0 on a lattice. When is the first time I reach the origin? It's just every time the walker only goes left and right, right? So the fastest time is this walker keeps going all the way towards the origin. So it will need at least that many steps, right? So in the discrete case, this will be 0 all the way there, right? Because you cannot reach if I start from here and I have to reach there, and if I take a time at discrete step, I cannot reach a time before that, right? That many steps I have to take. So there it will be 0 here, strictly 0, and then you will have this function, which will go like still at the tail, it will go like that, but details will be slightly different. Huh? X0 square. So, okay, so this is basically this thing. So this is one way of doing thing. I didn't have time, so I will not go through this. This is what we did it from there. But actually you can compute these probabilities. Again, you can write down an equation for each of these, like survival probabilities or this your first basis time probability. You can write down a directly equation and solve those equations, right? Because you might have some other problems with. You can also write something called back Fokker-Planck equation. I think maybe David might talk about it. Basically, since you don't care where the particle is at the end, so what we do is, instead of writing this, so the way we write down this Fokker-Planck equation, we took this time t and then we basically took a jump at the end. But what you can do is you take this thing, t plus delta t, you just consider the first jump in time delta t, and then you go from there. Okay, so that's called a backward Fokker-Planck equation. Okay, and then you have to solve those equations. Okay. You guys are tired, I guess, right? Okay. Do you have any questions?